In Unit 1, we learned that conservative forces allowed the two-way conversion of kinetic and potential energies. Just like kinetic energy, we will find out here whether momentum is obeying conservation or not. As shown in the figure below, imagine there are two particles, E and B of masses, m sub A, and m sub B, and they are isolated from other bodies. They move toward each other so that an interaction or collision may occur. Before collision, particle A is moving to the right, at an initial velocity v sub A1, while particle B moves to the left, at v sub B1. As soon as they touched, they interact, and from Newton's third law, each particle will experience a mutual force due to other particle. During interaction or collision, particle A will experience a force, F sub B on A, exerted by particle B. Consequently, particle B experiences a force, F on B, exerted by particle A. Their two forces, according to Newton's third law, are equal in magnitude but opposite in direction. For an isolated system, no other external forces acted on these two particles, therefore the sum of these two forces is zero. Since each particle experiences a force, both particles accelerate with A sub A, and A sub B. So from Newton's second law, the equation becomes mass of A times acceleration of A, plus mass of B times acceleration of B, equals 0. So right after collision, the velocities of particles A and B changes to v sub A2, and v sub B2, respectively. From Unit 1, we learned that acceleration is the rate of change of velocity of a body. Transforming acceleration in terms of velocities and time interval, delta t, the equation becomes mass of A, times the change in velocity of particle A, over delta t, plus mass of B, times the change in velocity of particle B, over delta t. From here, we can cancel out delta t. Then, we further simplify the equation by combining the initial velocities on the left side of the equation, and the final velocities on the right side. Here, we see an expression of momentum, mass times velocity. Now, take a look on this. The left side of the equation is the total momentum of the particles before collision, while the right side of the equation is the total momentum of after collision. With these, we see that momentum is a conservative quantity. Conservation of momentum states that, whenever two or more particles in an isolated system interact, the total momentum of the system does not change, that is the total momentum of the system before collision, is equal to its total momentum after collision. Conservation of momentum applies when an archer fires the arrow using a bow. He may experience a recoil. Firing a rifle causes greater recoil on marksman than the archer. Conservation of momentum is also the reason why the boat moves backward relative to the person as he steps on the duck. We can also see conservation of momentum on collision of cars. Now, let us give a sample problem on conservation of momentum. Problem number 4. A 60-kilogram archer stands at rest on frictionless ice, and fires a 0.03 kilogram arrow horizontally at 85 meters per second. With what velocity does the archer move across the ice after firing the arrow? So let us analyze the problem. Let's say that body A is the archer. Her mass is 60 kilograms. She is standing at rest on ice, therefore her initial velocity is 0. Then, we designate the arrow as body B, and its mass is 0.03 kilogram. Its initial velocity is also 0, since the archer is still holding it for a while. Then, she releases the arrow, so this 85 meters per second is the arrow's velocity after firing. What we are going to find out is the recoil velocity of the archer, v sub A2. So let us solve this. Since the archer is standing on a frictionless ice, we can consider this as isolated system, and no other external force acts on the archer and the arrow, except the mutual forces between them during firing. So we can use conservation of momentum. The total momentum of the archer and the arrow before firing, is equal to the total momentum of the system after firing. So since the initial velocities of both the archer and the arrow are both zeros, therefore, the total momentum of the system is zero. So we can eliminate these two expressions. From here we solve for V sub A2. V sub A2 is equal to the negative of mass of B times VB2, divided by mass of A. Substituting the given information, therefore, the velocity of the archer after firing the arrow is negative 0.0425 meter per second. This negative value indicates that the archer moves backward relative to the motion of the arrow. This backward motion is commonly termed as recoil. We have learned that conservation of momentum can be applied to analyze collision of bodies. And when we say collision, it refers to an event during which two bodies come close to each other and interact by means of force. Depending on situation and nature of colliding bodies, any of the three types of collision may occur: elastic collision, inelastic collision, or perfect inelastic collision. Now let us analyze first elastic collision. Elastic collision is one in which both total kinetic energy and total momentum of the system are the same before and after the collision. Hence, both momentum and kinetic energy are conserved, that is, the total momentum before collision is equal to the total momentum after, and the total kinetic energy before collision is equal to the total kinetic energy after. Here we have a model of two bodies A and B that move toward each other. Before collision, body A moves to the right, while body B moves to the left as indicated by given initial velocities, v sub A1 and v sub B1. For as long as these two bodies move, they possess momentum and kinetic energy. The total momentum before collision is represented by this expression, while this expression is for total kinetic energy before collision. After collision, they move apart with final velocities, v sub A2 and v sub B2. Again, for as long as these two bodies move, they possess both momentum and kinetic energy. This expression is the total momentum after collision, and this is also equal to the total momentum before collision. On the other hand, the total kinetic energy after collision is given by this equation. To illustrate clearly the mechanism of elastic collision, consider a ball A that is released at a certain height, h sub 1. Due to gravity, it falls, converting its potential energy into kinetic energy, and eventually will collide on the ground B. As it hits the ground will exert a force that causes the ball to bounce. If it bounces back to a height h sub 2, which is also equal to the original height, h sub 1, therefore its kinetic energy is converted back to its original potential energy. Thus the two-way conversion of potential and kinetic energies is observed all the time. Hence, an elastic collision happened between the ball and the ground. Here is another example. Imagine there are two cars, car A and car B, of the same mass. As you can see, car A is located at the back of car B. Let's say that, before collision, car A moves to the right, while car B is initially at rest. Therefore, only car A possesses kinetic energy. But as soon as car A hits car B begins to transfer its kinetic energy to car B. If there is no any deformation happened on these two cars, then all of the kinetic energy of car A will be completely transferred to car B, until it loses all of its energy. At this point, car A stops, while car B will move to the right at a velocity same as of the velocity of car A, just before it hits car B. Therefore, elastic collision occurs between the cars. Remember that, in elastic collision, the two colliding bodies separate after collision, they do not get stuck after collision. Also, no deformation happened on the collision surfaces, that's why all of the kinetic energies of the bodies are conserved, and did not transform into other forms of energy such as sound and heat. Now, let us proceed to another type of collision. The inelastic collision. Inelastic collision is one in which only the total momentum of the system is the same before and after the collision. Hence, kinetic energy is not conserved, that is the total kinetic energy of the system before collision, is greater than after collision. Some of the kinetic energy before collision has been lost, and converted into some form of energy, such as deformation of colliding bodies, sound and heat. This loss of kinetic energy is denoted by E sub loss, and that is equal to the difference between the total kinetic energy of the system before and after collision. We see that, inelastic collision has similarity with elastic collision. The two colliding bodies also separate after collision. They do not get stuck after collision. In what aspect they differ? They differ on how efficient the kinetic is conserved. In elastic collision, kinetic energy is conserved, while in inelastic collision, deformation may be observed on the surfaces of colliding bodies after collision, and sound and heat may be produced also. These things contribute to the loss in kinetic energy. In fact, elastic collision is almost impossible to happen. What we usually observe is inelastic collision. Again, when a ball is released at a certain height, it bounces to a height less than its original height. Therefore, the two-way conversion of potential and kinetic energies is destroyed. The kinetic energy of the ball as it hits the ground is not completely transformed into potential energy, rather it is transformed into other forms such as deformation of the ball. Sound and heat may be also produced between the ball and the ground. These are the reasons why the ball bounces to a lower height. This is also the case in collision of cars. The kinetic energy of car A is transformed partially into kinetic energy of car B. The remaining amount is converted into some form of energy that causes deformation, sound and heat. The third form of collision is called perfect inelastic collision. It is a type of collision when the colliding bodies stuck or entangled after collision, and they move as one body. In this type of collision, only the momentum is conserved, while the kinetic energy is not. Now, take a look on this. Since after collision, the two particles stuck or entangled, they move at the same velocity, v sub 2. Therefore, their total momentum after collision is their combined masses, m sub a plus m sub b, multiplied by v2. In terms of energy aspect, once the bodies stuck together after collision, their kinetic energies before collision will be converted largely into other forms of energy, such as heat, sound and deforming energy, which contributes to the loss of kinetic energy. Collision may also occur in two dimensions. Depending on type of collision explained above, the presented formulas may be also used. However, the process may be long, since we need to analyze separately the conservation momentum in terms of x and y axis. Let us consider this model. As you can see, before collision, particle A moves to the right while particle B is at rest. As particle A hits particle B at this collision point, and assuming elastic collision occurs, then they immediately move apart. So after collision, both particles move at an angle from the horizontal, alpha and beta, that make our analysis of collision in two dimensions. In actual problem solving, it is necessary to determine first the x and y components of the velocities before and after collision, before applying the conservation of momentum equation. We have just learned the three forms of collision. Now, there is a single number that describes what type of collision is happening on the system, called coefficient of restitution, denoted by small letter e. It is a measure of the elastic properties of colliding bodies. Mathematically, it is the ratio of the negative of the relative velocity after collision and relative velocity before collision. And that is negative of the quantity, v sub a2 minus v sub b2, all over, v sub a1 minus v sub b1. The value of the coefficient of restitution varies from 0 to 1, depending on the type of collision. For elastic collision, the value of E is 1. Any value greater than 0, but less than 1 is for inelastic collision, and for perfect inelastic collision, 0. Take note that this equation of coefficient of restitution is very helpful in dealing with elastic and inelastic collision. Do you have any question in mind? Just let me know. In solving problems involving collision, one thing you shouldn't forget is to identify clearly what type of collision is happening between bodies. After identifying the type of collision, you should think of the given information such as masses and velocities. Then apply the conservation of momentum equation, as well as the equation of coefficient of restitution. Good luck. Okay class, it is time for us to solve problems involving collisions. Problem number 5. A 1,800 kg car stopped at a traffic light is struck from the rear by a 900 kg car. The two cars become entangled, moving along the same path as that of the originally moving car. If the smaller car were moving at 20.0 meters per second before the collision, letter A, what is the velocity of the entangled cars after the collision? Letter B, determine the total kinetic of the two cars before and after collision. Now let us try to analyze the problem. Imagine this is the 1,800 kg car, and we assign this as car A. This car is stopped at a traffic light, so its initial velocity, v sub a1, is 0. From its rear, there is another car of 900 kilograms, and this is car B. After car B hits car A from rear, they become entangled, so the type of collision is perfect inelastic collision. The velocity of car B is 20 meters per second just before collision, and that is v sub b1, equals 20 meters per second. We are going to letter A, the velocity of the entangled cars after collision v sub 2, and letter B, the total kinetic of the two cars before and after collision. Now let us solve. For v sub 2, we use the conservation of momentum formula for a perfect inelastic collision. Mass of A times v sub a1 plus mass of B times v sub b1. So this is the total momentum of the two cars before collision. This should be equal to the total momentum after collision, that is the total mass of A plus mass of B, times the velocity of the two car after collision. Since v sub a1 is 0, so we can eliminate this. So from here, we solve for v sub 2, by dividing both sides by the total mass. So v sub 2 is mass of B times vb1, divided by m sub A, plus m sub B. The velocity is 6.67 meters per second. So this is the velocity of the wreckage after collision. For letter B, solving for the total kinetic energies before and after collision. The kinetic energy is 1/2 mv squared. Since car A is initially at rest, so it has no kinetic energy, therefore we can eliminate this from the equation. So the total kinetic energy of the two cars is only the kinetic energy of car B, that is 1/2 of mass of B, multiplied by the square of v sub b1. Substituting values, so the total kinetic energy before collision is 180,000 joules, or that is 180 kilojoule. For the kinetic energy after collision, we should expect a lower value than 180,000 joules. Since the type of collision is perfect inelastic, we have learned earlier that the kinetic energy is not conserved. Again, we use the same formula, 1/2 mv squared, that is 1/2 of the total masses of cars A and B, multiplied by the final velocity, v sub 2. Substituting the values, so the total kinetic energy is 60,060 joules. As expected, our answer is less than the kinetic energy before collision. Almost 120,000 joules of the kinetic energy has been converted into heat, sound, and deformation of cars, due to impact. In previous problem, we see how deal with perfect inelastic collision. Now, in this problem we are going to take a look on elastic collision. Problem number 6. A block of mass m sub A equals 1.6 kg, initially moving to the right with a speed of 4 meters per second on a frictionless horizontal track, collides with a light spring, attached to a second block of mass, m sub b equals 2.1 kilogram, initially moving to the left, with a speed of 2.5 meters per second, as shown in the figure below. The spring constant is 600 newtons per meter. Letter A. Find the velocities of the two blocks after the collision. Letter B. Determine the velocity of block B during the collision, at the instant block A is moving to the right with a velocity of 3 meters per second. Letter C. Determine the distance the spring is compressed at that instant. Letter D. Determine the maximum compression of the spring. Now, let us establish the given information. Mass of block A is 1.60 kg. Its initial velocity, v sub a1, is 4 meters per second. Mass of block B is 2.1 kg. It is moving to the left at a velocity of v sub b1 equals -2.5 meters per second. Then this spring has a constant value of 600 newtons per meter. And we let the initial position of the spring, x sub I, to be 0, since it is initially at equilibrium position. Now, let us think of what type of collision is likely to happen. Since there is a spring attached to block B, therefore the two blocks will definitely move apart after collision. And the spring makes the conservation of kinetic energy more efficient. Therefore, we can safely assume that this type of collision is elastic. Now what we are looking for is letter A, the velocity of each block after collision, VA2 and VB2. Letter B, the velocity of block B, VB2, if VA2 is 3 meters per second. Letter C, the spring compression, X sub F, if VA2 is 3 meters per second. And letter D, the maximum compression of the spring, X sub F, if the blocks stopped. That is, their velocities, VA2 and VB2, are both zeros. Now that we have identified all given information and quantities to be solved, let us begin the solution. We begin with the equation of conservation of momentum for elastic collision. The total momentum before collision is equal to the total momentum after. We substitute all those with given information. We have mass of A, 1.60 kg, VA1 is 4 meters per second, mass of B is 2.10 kg, and VB1 -2.50 meters per second. Then, for the right side of the equation, again, mass of A is 1.6. We do not know yet VA2, so we just rewrite it for a while, then we add MB, 2.10, and finally, we rewrite again VB2 because it is still unknown as of this moment. We further simplify. If we evaluate this, the total momentum of the system before collision is 1.15 kg per second. Remember, we have two unknown quantities here, VA2 and VB2. So we need to construct one more equation. But before that, we can solve here either VA2 or VB2 in terms of the other. Let's say we solve for VB2, so this equation becomes VB2 equals the quantity, 1.15, minus 1.6 of VA2, divided by 2.10. Again, we do not know yet VA2, so we cannot solve immediately for VB2. Don't worry, we label this as our equation 1. Now, we begin to construct our second equation. We will use this equation of coefficient of restitution as our second equation. Then we substitute known quantities. For the value of E, since the type of collision is elastic, its value is 1. We rewrite VA2 and VB2, VA1 is 4 and VB1 is -2.5. Simplify the equation, then solve for VB2. So VB2 is VA2 plus 6.5. Finally, we have constructed our second equation. What we do next is we equate our first and second equation. This expression came from equation 1, while this one came from equation 2. Notice that in this equation, we have only one unknown quantity, that is VA2. Isn't it amazing? From here, using a little more manipulation of equation, and solve for VA2. So VA2 is equal to negative 3.38 meters per second. Then we go back to either equation 1 or equation 2 to solve for VB2. Let's say, we use equation 2, because it looks much easier. So from equation 2, we simplify and substitute the value of VA2. At last, VB2 is equal to 3.12 meters per second. We observe that, after collision, block A moves to the left, since the value of VA2 is a negative, while block B will move to the right, since VB2 is a positive. Now, for letter B. We will solve for the velocity of block B, when block A is still moving to the right at 3 meters per second. Take note that this scenario happens during collision, since block A is still in contact with the spring. Again we use the conservation of momentum equation. We substitute given information. This is much easier since we have already the value of VA2, so we only one left unknown quantity, and that is VB2. Solving for VB2. VB2 is negative 1.74 meters per second. Since this value is a negative, therefore block B is still moving to the left. It means that the spring is not fully compressed. In fact, blocks A and B still have kinetic energies to further compress the spring. For letter C, we are going to solve for the compression of the spring, X sub F, at instant block A moves at a velocity of 3 meters per second. To solve this, we will go back to Unit 1. We know that in order to compress the spring, work must be done. And that work is given by the equation, 1/2 of the spring constant K, multiplied by the difference of the squares of X sub F and X sub I. We can eliminate here X sub I, since it is 0. From here, we solve for X sub F, so X sub F is equal to the square root of 2 times the work done W, divided by the spring constant K. Now, we label this as our equation 3. In order to solve for XF, we need to solve for the work done. So let us analyze this carefully. What energy causes the spring to compress? Of course, these two moving blocks causes the compression of spring. So it is the kinetic energy of the system that makes this spring compression. Therefore, the work done on the spring is equal to the negative of the total change in kinetic energies of the two blocks. We put here negative to make the work done positive, since both delta K of blocks A and B are negatives. This expression is the change in kinetic energy of block A, while this one is for block B. Then, substituting the values. So the work done on the spring is 8.98 joules. After this, we go back to equation 3, then we can now solve for the compression of the spring X sub F. So the spring will be compressed by 0.17 meter. Or that is 17 centimeters. Take note that this value is not the maximum compression, since we have solved this when the two blocks are still in motion. Now for letter D, we are looking for the maximum compression of the spring. It will happen at instant the blocks come to rest. It means that all of the kinetic energies of the blocks is converted into the work done on the spring. From letter C, we will use again the equation of work, but this time, VA2 and VB2 are zeros. Substituting all given information, so the maximum work done is 19.36 joules. Then, we go back to equation 3, and solve for X sub F. So the maximum compression of the spring is 0.25 meter. At this point the spring no longer be compressed. The kinetic energies of the two blocks are converted into elastic potential energy of the spring. Then, the spring will start to convert this potential energy back into kinetic energies of the blocks, to keep them apart right after the collision. Now it's your turn. Let us see what have you learned. Exercise number 2. Two blocks A and B move toward each other, on a frictionless horizontal surface. Before collision, block A moves to the right at 5 meters per second, while block B, to the left at 10 meters per second. If the masses of blocks A and B are 7 kilograms and 5 kilograms, respectively, find letter A, the velocities of blocks after collision, if the collision is inelastic, with a coefficient of restitution of 0.6. Letter B, the total kinetic energy before and after collision, and letter C, the energy loss. Good luck. Congratulations for reaching this last problem. Now, we are going to consider collision in 2 dimensions. Let's keep up. Problem number 7. A small compact car with mass of 1,000 kilograms is traveling north at 15 meters per second. At the intersection, it collides with an enormous luxury car with mass 2,000 kilograms, traveling east at 10 meters per second. Fortunately, all occupants are wearing seat belts, and there are no injuries, but the 2 cars thoroughly tangled, and move away from the impact point as one mass. What is the velocity of the wreckage after collision? Now let us carefully analyze this. Imagine this is the small compact car. We label this car as car A, with a mass of 1,000 kilograms. Initially, it is traveling north at 15 meters per second. This is the enormous luxury car. We label it as car B, with mass 2,000 kilograms. Traveling east at 10 meters per second. Let us say that this 2 car will collide at this point. As you can see, this is the car A that moves on y-axis, while car B that moves along the x-axis. And according to the problem statement, the car is entangled and they move as one body, so this problem deals with 2-dimensional, perfect inelastic collision. What we are trying to solve is the velocity of the wreckage, that is v sub 2. So after collision, what do you think will happen? In what quadrant they move as they collide? Is it on the first quadrant? Or maybe, on the second quadrant? Come on, think. Do you think the car will move on the third quadrant? I guess not. That is close to impossible. How about on the fourth quadrant? What do you think? Very good, the 2 cars are likely to move on the first quadrant, as soon as they collide. What we are going to solve is the velocity, v sub 2, right after they collide. Of course, we will also include its direction, theta sub x. Now, let us solve, to see if our prediction holds true. The first thing we do is solve for the x and y components of velocities. For the x and y components of VA1, by observation, VA1x is 0, since car A is only moving north, or along y-axis. With this, VA1y is already equal to positive 15 meters per second. For the x and y components of VB1, again by observation, VB1x is already equal to positive 10 meters per second, since car B is purely moving on x-axis, while the y component, VB1y is 0. After solving for the components of the velocities, we are now ready to solve for the x and y components of the final velocity, v sub 2. We use the equation of conservation of momentum, for perfect inelastic collision. From this equation, we solve for v2x. That is mb times vb1x, all over the sum of masses, ma, plus mb. Substituting the given information. So, v2x is positive 6.67 meters per second. Since this is positive, therefore v2x is towards east, same as the direction of car B before collision. For the y component of the final velocity, v sub 2y, we will do the same process. Using the conservation of momentum for perfect inelastic collision. From here, we solve for v2y. So v2y is m sub a, times va1y, divided by ma, plus mb. Substituting the values will give, v2y equals positive 5 meters per second. Notice that this is positive, therefore this is towards north, same as the direction of car A. With this, we can definitely say that, v sub 2 is on the first quadrant, and that the wreckage will move along this direction. And this agrees with our prediction earlier. Wow! Can you see that our common sense agrees with these mathematical approach? And that's the essence of our study, it justified our common sense. Now we are ready to solve the magnitude and direction V2, using Pythagorean theorem. Substituting the components, the magnitude is 8.34 meters per second. For its direction, theta sub x, we use the inverse tangent of the ratio of v2y and v2x. Substituting the values, so the direction is 36.9 degrees north of east. Therefore, the wreckage moves at a velocity of 8.34 meters per second, 36.9 degrees north of east. That's it. Do you have any question in mind? Kindly communicate with your teacher. You can now answer your problem set number 4 completely. And prepare for a quiz. Keep safe and God bless us all. See you later.